Thank you very much for inviting me this evening. I think what's going on here is really terrific, really exciting. When I was 16, I was told by my high school that I could be an artist or I could be a scientist. And I said, damn it, I want to be both. And I went to see we call him the headmaster, I think you call him the principal. And they got the schedule out and they spread it out on the table. There's absolutely no way on earth someone can take art and chemistry or art and physics. Everybody knows the two are so incompatible. So here we are, and this is wonderful. And Christina's talk, she's dealing with the flotsam and jetsam of our culture. Would you argue with me? Where's she gone? Has she gone home already?
No.
Well, she's
right here.
Oh, hi. Oh, you put a coat on and camouflage or something. Is that okay? You're dealing with the flotsam and jetsam of our culture. I will argue I'm dealing with the flotsam and jetsam of the solar system. and so Christina takes this stuff out of the trash, and I take my meteorites from wherever I can get them. Sometimes that's the trash. Literally, we found meteorites in dumpsters before. And then we try and do something beautiful with them. I don't use a ballpoint pen, but I use other tools, and so I do use a ballpoint pen, but not with such eloquence. But we work on them, and we try and come up with intellectual constructs, creative constructs, in a way not too dissimilar from the drawings we've just been looking at. But sometimes we're not quite so eloquent in how we say things. But I think I've always thought since I was 16 that what's going on up here is very, very similar. So I'm Derek Sears. I was born in the United Kingdom, as you may have determined. Came to the United States when I was 30. Brought my wife and my children. My child, we made a few more when we got here. Spent my life predominantly in the United States, predominantly as a member of faculty at the University of Arkansas, where I started out as a professor of chemistry, and then I gradually morphed back to my childhood passion, which was one of my childhood passions, which was space. The other being women, of course. sorry, darling. So you know, what does a chemist do who really wants to do spacey things? When you think about it, you've got to do something at the lab bench, and the only way you can deal with space is to deal with these strange rocks that come from space and land on Earth. So I ended up being a meteorite person right from the days I went to college, my grad school. And then about 2 years ago, we decided we'd had enough of the wonderful state of Arkansas. We'd done a lot of really terrific things, but we suddenly discovered the Bay Area. Our son came out here to school, and he met a wife and had a baby, so we became grandparents just 2 years ago. But it also gave me an opportunity to do some new exciting things with my professional career. So we went down and saw the folks at NASA and just banged on the door and will you let me in? And here I am. So now I'm a research scientist at NASA Ames, and I'm still working on meteorites. So other than I don't see a whole bunch of students at NASA, but as I did at the university. But other than that, I'm living a very similar academic life. Maybe I have a few deans to worry about and a few administrative committees to worry about. But so I do more hard science. So I'm going to tell you a little bit about meteorites, and I hope that you get some inkling of what I'm trying to say when I say what Christina and I do, I think, are not so different. So what do I do with this thing? I press the middle button, and nothing happens. One button. Okay. He's a rocket scientist, he doesn't know how to use the remote. Oh, there we are, we're back again. Let's try and go forward. Try and go backwards.
Could be.
Christina! Can we show you how to use the technology? Now make it move. Make it move.
Make it move.
Make it move.
I would like them to press it.
Where's Christina? She seems to have no problem.
Yeah.
Can I use the machine over here?
Of course. You want to run the video?
Yeah.
There you go.
It's moving pictures. Thank you. This is a meteorite fall. Since video cameras became so commonplace and people with all these handheld devices, we've started to get pictures of this miracle of a rock coming out from space, entering the atmosphere, crashing to the surface of the Earth. These spectacular events, you can imagine, look at this for targets. How does that feel to somebody who lives on the West Coast? And there's the impact point. I can play that again, just because I like it. This is a meteorite that fell in 1993 in New York. Oh, it landed in New York, was seen over most of the central portion of the United States. It came in at something like 30 kilometers a second, moving at a truly interplanetary speed. At about 40 kilometers up in the atmosphere, it started to warm up, got down to about, 30,000 feet, let's say. The thing started to produce this huge ball of ionized air around it. And they say that if the meteorite's a football, the fireball is a football field. Give you a sense of how much energy is being dumped into the atmosphere. So you take the atmosphere up to phenomenally high temperatures. It's so hot you're not even sure if you can still think of it in terms of temperature. You can't measure it with a thermometer. It's ionized gas, it's a plasma. Produces huge amounts of light, lots of visual effects. And then it hits the sound barrier. You hear sonic booms, and then it goes out, and then it just falls like a block of concrete. As it's coming through the atmosphere, as you saw, fragments into a million pieces, fragments into a large number of pieces, because this is a rock that's come from space that's full of cracks, and as it gets through the pressure of coming through the atmosphere, each piece breaks away, so you get 20, 30, 40, 50,000 sometimes of fireballs, and each one will make a sonic boom. So people say that people who've heard these things, which are usually anybody but the meteorite specialists, right? So the people who hear these things, meteorite people who never see a fireball, say it's like a battle going on in a field next, boom, 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 boom. So it's cannons firing at one another. So somebody else said it was like I don't know if this metaphor works for us anymore, but a cart being drawn, horse-drawn cart that's going across cobblestones. It sounds like that, but very, very, but deafeningly loud. There's the point of the impact. This, an undergraduate student at one of the New York colleges owned this car. It's a used car that she paid $100 for it to get her to and fro from home to. We've all been students at one point, right? So, first car, $100. And she came out one morning. And this is what she found. In fact, that's a better picture. She sold the car for $10,000 to a meteorite dealer from Tucson. And she sold the meteorite. Here's the meteorite. You can see it's basically a pale grey. This is a little overexposed. It's a pale grey interior, silicate minerals, just a rock. And then it's got this black fused coating on it. They call it the fusion crust, where as it came through the atmosphere, the surface got hot and melted. So it's a black glass that's produced. It's not too dissimilar from the heat shields on spacecraft. But you see what? It's incredibly thin. It's less than a millimeter thick. Isn't that amazing? So this meteorite came through the atmosphere, produced ionized gas that was the football field size, went through this incredible event, and then the damage was only skin deep. So you see that? So just the very, very surface got heated, the interior is pristine. So here we are sitting on Earth, and we're having these things fall down on us or come crashing into us. And they're not really getting altered much through that horrible passage through the atmosphere. But then I guess the astronauts don't get altered much as they come down through the atmosphere normally. She sold the meteorite to the same dealer from Tucson for $100,000. So my students wanted to get a block of concrete and go outside and smack them into my car and see if they could get this dealer to. So these are the flotsam and jetsam of the solar system. These are just rocks that are floating around out there, and by random processes are occasionally falling on Earth. And we get them into the they go into the museums, they sit there, they go out into the research labs. At NASA, we've been recovering some of these. I'll get to that story in a moment. It's remarkable. But when we take the rocks apart, we see some amazing things. This is actually, we're having a lot of success finding meteorites in the deserts of North Africa. There are dealer, hunter people getting expeditions and going out into the Sahara Desert and to some of the other regions of North Africa, some in Oman, and then there's a handful of people in Australia out the Nullarbor Desert. And they're finding meteorites in the desert where they've been able to survive. And they stand out quite distinctly among the local rocks. They usually, for one thing, often they look black. Those that don't look black look conspicuous. And so you sort of can easily identify them if you've got your eye in. And you bring them back and you sell them to American mineral dealers, collectors, for large sums of money. Okay? This particular rock was from North Africa as a DAG 943. Just named, some committee names these things. It is, for all the world, like a basalt, sort of things that comes out of volcanoes on Earth. So we have a chunk of basalt. Now we can do various tests on this thing. We can do various measurements. If we look at the light that's reflecting off this stone, it looks exactly like the light that's reflecting off the major asteroid Vesta. It's the fourth largest asteroid. And as you probably know, the asteroids are a belt of rocks in between Mars and Jupiter out there in the solar system. Very unusual asteroid. It's big. It's almost spherical, roughly spherical. Just been visited by a spacecraft. This is a spacecraft image. And it's a very unusual asteroid. Not very many like it. So we have this rare asteroid, big, way out, and we think we're having pieces of it fall on Earth. Okay? So this is a basaltic meteorite. I think if I were to get rid of the fusion crust, take a piece from the inside, just give it to a geologist who's not really seen many meteorites, he'd say, oh yeah, it's a basalt. It's not that strange. What's strange about it is it didn't come out of a volcano on Earth, it came out of an asteroid 30 million miles away, or more. Here are some other cool meteorites. This one with I love these things. It's absolute. You see these in a museum and you can't put them down. They've got this dense, black, glassy, shiny fusion crust. You want to make a necklace out of them. They're really, really pretty. And in fact, my wife does have a necklace made of a meteorite. We don't take it to conferences. That would tick people off. But, so here we are. This is a very distinctive looking meteorite. The first one of its sort fell in India in the 1880s. 1863. But this is another basalt, but it's a slightly different basalt chemically. And this one is really unusual because if you take this meteorite and you get rid of the crust and you heat it up in a furnace, and then you collect the gases that come off, the mixture of gases that you get out of this rock are absolutely bizarre. They're like nothing you see anywhere else. And we have, when this was done, it was actually done by some NASA people in Houston, the Johnson Space Center, who got their PhD at the University of Arkansas, I hasten to add. When you take these gases out and you see this bizarre pattern, nitrogen is up and argon is up, one thing and another. The sound goes on. What's that? The light goes on. There you go. The light bulb goes on. That is the atmosphere of Mars. And we know what the atmosphere of Mars is like because the Viking spacecraft landed there in the 70s, 1976, right? 4th of July or some such thing, I'm not sure. It actually landed on Mars, sucked in the gas, put it through a mass spectrometer, gave us a composition. And we've known that composition, it's in the textbooks, we've known it since 1976. Very odd, very strange. All the planetary science graduate students got it memorized. put this piece of rock into the lab, and the same composition came out. And then you piece a few other things together. It's a volcanic rock. It's young, 1.5 billion years, much younger than normal meteorites. It has to come from a geologically active planet. The crystals are laying down like they settled in a gravity field. See, this was a big planet these rocks came from. Anyway, these came from Mars, no doubt about it. We have about 60 to 70, depending on how you count the fragments, meteorites on Earth that came from Mars. Okay. Now, I've told you all that. Do not tell Congress. Because NASA's trying to squeeze $300 billion out of Congress to go to Mars and get rocks. I say that very facetiously. These are the flotsam and the jetsam, right? The big frustration is we don't know what geological context they came from. And that's a biggie, okay? Now here's a rock. This is really unusual. We do not see these rocks in terrestrial contexts. What you have here is a basalt, been melted, a very unusual melting process. We do see that happen a little bit on Earth in a crater. So we think this has been through some sort of impact cratering type process. But these things, you do see them on Earth in trace amounts, very, very rare. You see them in Greenland a little bit, you see them in the Antarctic a little bit. But here they are, great big chunks of the stuff mixed in with basalt. We never see them, the terrestrial anorthosites, these terrestrial white rocks. You don't see those associated with basalt on Earth. And you certainly don't see this sort of shot. And again, this is one of those stories, a bit like the Mars story. A bunch of scientists got this meteorite from the Antarctic. Wonderful name, Allen Hills 81004. Rolls off the tongue, doesn't it? Well, there's so many meteorites, they can't just name them, they have to put these numbers on. And anyway, it's from the moon. 20 or 30 labs that got this rock for a preliminary examination in 1985, 6, stood up at a conference and every one of them said, guess what guys, I've made a major new discovery, this is from the moon. And 20 of them in a row said that. You don't get that at conferences very often. So we also have, now again, it's something on the order of 60 meteorites, which are fragments of the moon. So flotsam and jetsam, rocks falling on Earth, and they're coming from cool places like the major asteroids, the moon, and Mars. But again, it's the flotsam and the jetsam, and when a geologist works on the history of a rock, the first thing he says is, where did it come from? What was the geology of the source region? What rocks were sitting on top of what rocks? And how they arrange with respect to each other. You know the story on Earth where you have plates and you have oceanic crust and continental crust and volcanism, you have all sorts of things going on. And then you have these vast sedimentary rocks, sandstones, limestones. Very different history, very different story to tell. And you get a rock from any one of them, you can't really say a whole lot if you can't put them in context. So that's a problem. But we have Mars rocks, we have moon rocks. And now the best ones of all. These are the ones I study. Be kind enough to get me a cup of water. My mouth's going to seize up any moment. These are meteorites which are not of the sort I've just been saying. Right? These are not from Vesta. These are not from the Mars. These are from everywhere. So these are rocks which seem to be from. Oh, fantastic. Between Mars and Jupiter, out there in space, we have something on the order of 200,000 rocks. Right, the asteroid belt. Something on, some of them are very, very small, but we have something on the order of 200,000 asteroids. And we put the telescope, we can only see a small percentage of them, most of them are too small. We put a telescope on them, we get the spectrum, we try and figure out what they are. And they're this and they're this. but there's thousands of them, hundreds of thousands. And these rocks, almost certainly, are coming from them. So we don't have planetary geology to work with. We have this solar system dust, or solar system debris to work with. Here's one that fell just a few months ago in gold country here. This one's in Antarctica. This is from Antarctica. And these are asteroids that we visited with spacecraft. So these, as far as we can tell, with our present state of knowledge, these are pretty much what these asteroids look like. They're not great big spheres like planets. They're irregular little rocks, pieces and fragments of rocks. They're too small to form themselves into spherical planets. They're heavily cratered. Some of them have got craters which are as big as this object. Can you imagine that? You have an object that big and it has a crater on it. That, you know, the diameter of the crater is equal to the radius of the target. So massive. Why didn't it fragment? And why didn't it just shatter? There it is. Little pieces, splinters. This one is a near-Earth object. This has the potential to hit the Earth at some point. It's a near-Earth object. There's a crater. This thing actually looks like it got hit and bent. They've all been visited by spacecraft. Here's some details. All sorts of craters, but look, a sort of smooth look to them. So they're cratered, but they're covered in dust to subdue the cratering texture. So we have heavily cratered, very dusty, lots of little boulders. We have dark areas and light areas. We have these strange stretch marks here. So this is just a picture taken real close up as the spacecraft was crashing. So boulders, clods of earth. So we can get some sense of where these rocks came from just looking at these pictures. Right? Now, these are the common meteorites. In my opinion, they're the most interesting meteorites because they don't come from a planet. And they have been the subject of phenomenal study. This is a who's who of chemistry. Right? Do you recognize some organic chemists up there? Zalius, father of organic chemistry. Right? Harold Urey's gone off the end there, Marie Curie. Antoine Lavoisier. Any of you know who Lavoisier was? Any of you know who Newton was? Sir Isaac Newton. Lavoisier was chemistry's Isaac Newton. Lavoisier was the one who said we can do chemistry. All these very distinguished, by that I mean he figured out the basic ideas of a reaction. So much of this reacted, so much of this to give so much of this. That's Lavoisier. And then he was a victim of the French Revolution in his prime. But anyway, the distinguished line of chemists and mineralogists that have worked on these particular meteorites, and by this hard work, starting out with Bunsen burners and blow lamps, blow torches, ending up with mass spectrometers, have deduced a phenomenal amount of information about these rocks. So when I tell you that we study the chemistry of these meteorites, we call ourselves cosmochemists. We're not talking about stuff that was done in the last decade or two. We're talking about stuff that's been done over the last 200 odd years. Right? First meteorite studies, serious meteorite studies using chemical techniques, 1803. This is not a quote modern subject. This is not a 20th century subject. This is an ancient subject. But adding it all up over the years, here are the three major findings that we get for these non-planetary meteorites. First of all, if you compare their composition, this is the composition of the meteorites on a log scale. So this is 10 times this is 10 times this is 10 times this. On a log scale, with the composition of the sun, on a log scale, you get a correlation that most experimental scientists would give their right arm for. All right? So you see what I'm saying? These rocks that are falling on Earth from space, these flotsam and jetsam, that are not coming from planets, that are just floating around out there in the cosmos, have the same composition as the sun. Now, isn't that something? What? You've got basalts, you've got limestones, you've got all these rocks we've got on Earth. Nothing like any of them. They're nothing like anything we find on Earth. This is why I think these are much cooler than the planetary meteorites, even though the planetary meteorites are pretty damn cool. If we use our dating methods, I don't know how much detail you can suffer at 8 o'clock at night, okay, but rubidium decays to strontium, rubidium-87, beta decays to strontium-87. So, and it's like a clock ticking, decay, it's a clock. And to cut a long story short, as that's decaying to that, it produces a line, and that line gets steeper as time goes on, as more decay happens. So from the slope of that line, you can determine the age of the rock. Okay, you ready for a number? 4.57 billion years. That is roughly half the age of the universe. Okay, so these rocks, these rocks that are sun stuff, are incredibly old. There is half the age of the universe. But what's really odd about this is, if you do a whole rock analysis of the Earth, if you pretend the Earth is one rock, you get components from all over the Earth, and you do the same sort of dating. You know what number you come up with? 4.67 billion years. And if you go to the astrophysicists and you say, how old is the sun? And the astrophysicists now have got models, have got theories governed that sort of depend on the ratio of helium to hydrogen. The sun burns by hydrogen turning into helium. So it generates huge amounts of energy. You know, it's called like an atom bomb, right? it's like a hydrogen bomb. So the hydrogen bomb process is going on in the sun. From the ratio of helium to hydrogen, you can estimate the age of the sun. Guess what? 4.67 billion years. So, all right, we're seeing a pattern here, you know. The Earth, the Sun, the meteorites were all formed at the same time, right? Half the age of the universe. And the meteorites were formed from the same stuff as the Sun. So we're beginning to say, hey guys, we can actually, in our labs, we have rocks, we can look at them and we can see how the planets formed. Or at least we can look at something that was around when the planets formed, and that was probably formed by a similar sort of, or by the same process. It's pretty cool, isn't it? See, it's almost as cool as one of those immaculate ballpoint drawings in a different way. It's cool in a different way. And then, if you're a geologist and you like to look at these things under a microscope, you can cut a slice and you can put them under a microscope and you see something that you've never seen anywhere else before. Not only have they got a strange composition, but they're made of strange things. So glass beads, little glass beads. You don't see them in terrestrial rocks. You might see a bit of glass here and there. But these are little glass beads with beautiful crystal structures in them. Really make they wonderful, what do you call it, things on your computer, the wallpaper on your computer. Really pretty. You know? And then you have metal. Now that got the early chemists excited. We had rocks that had metal in them. You don't see that in terrestrial rocks because the metal rusts. You see iron oxides. You do not see hydroxides. You do not see iron. Native iron on the Earth is almost always meteoritic. So you can come along with a magnet. Sometimes these things are magnetic. That drives the scientists crazy because they can measure magnetism. You can go screw it up. There are sulfides, iron sulfide, never seen anywhere else. FeS, iron sulfide, in this meteorite in 5% by volume. Don't see it anywhere else. These sulfides on Earth are different minerals. They're sulfur polymers, basically. Quite different things. And there are these refractory inclusions, I'd call them, strange beasts. So they're sun stuff, they're as old as the rest of the solar system, they are strange under the microscope. And that signals some strange things were going on. Well, all right, I'm getting up against the time here. But we have some ideas, thinking about the sort of things I've been talking about. How did the sun form? How do we see stars forming in the cosmos? Well, we think we know. You have a great big nebula. You have periodic density fluctuations. Sometimes those density fluctuations go high enough that you get a little bit of gravity. Then it starts collapsing, and the more it collapses, the bigger it gets, the more gravity, the more it collapses, the bigger it gets, the more it collapses. So it goes up like that. Until eventually you get runaway accretion and the whole thing collapses. And then the thing's rotating. It's hard not to rotate in space. It's almost impossible if you're sitting there as a gas or any sort of object in free space. It's almost impossible not to rotate. Any little thing will set it off. And so the norm is to rotate. So you rotate and you collapse. And you're collapsing very quickly, you're rotating fairly quickly, you end up as a fried egg shape. And then that system gets crazy, it goes even more violent, eventually starts squirting out in the middle because it's been pushed up there. So you end up, so this is the scene. So we think this is the sort of environment that we're looking at for meteorites. And you know what scientists are like, you know what artists are like, detail, 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 right? So you dig into the details, and you try and figure out to what degree can you make all these properties from that nebula that's collapsing and rotating. A lot of things, some things work, a lot of things don't work. Now we get to the point that I'm telling you, we've got phenomenal amounts of information, exquisite types of information, but we're stumped. Okay? There's a whole bunch of reasons why they problems for making them in that nebula, that collapsing, rotating nebula. So, all right, we go to the asteroids. We say these were made on the asteroids. What went on the asteroids? We draw up a list of ways to make them, and then we run into problems there. These asteroids are too small to retain things if you smash them. And we get into all sorts of trouble when we try and relate the detailed properties of the meteorites with those environments. So we know we're onto something really, really major, and we know we can produce incredible amounts of data. We have equipment that is just so sophisticated you wouldn't have dreamt of it 10 years ago. So we're inventing modern equipment at a phenomenal rate, especially in Silicon Valley, right? We're inventing all this equipment, and we're getting more and more exquisite data, but we still keep bumping up against the brick wall. We're missing something. And what are we missing? We're missing context. We're missing the regional geology. So, this was some experiments we did at Arkansas. I just like showing off these pictures of Amber. Trying to figure out what happens in a gravity-free environment. So we took 4 of our favorite undergraduate students. We gave them travel pills, anti-sickness pills, put them on the plane, and they were all sick as dogs. But before they actually passed out, we got some work. So we had mixtures of, like they have in the meteorites, mixtures of metal and silicate. So we were shaking them about under weightless conditions, trying to see if we could reproduce some of these patterns in the meteorites. So we were fairly successful in producing some of the patterns that we weren't trying to do the whole thing. That picture keeps popping up in the most surprising places. It was used for an advert for a Russian travel agency. I opened the Sky and Telescope, and there was this Russian travel agency said, "Come to Russia and see the impact craters." And there was Amber. It's a NASA picture, so it's no copyright. But people really love that picture. She's now a very distinguished scientist with the Space Science Institute in Princeton. So we need to go to an asteroid. We need to do the geology of the asteroid, what's lying on top of what the structures are, what the whole layout is. And we need to bring back samples so we can do what we do best in the lab with the information we have about where they came from. We tried to do that. Well, the first thing we did was the Near-Earth Asteroid Rendezvous. We sent a spacecraft to this near-Earth asteroid, Eros. It's one of this group of asteroids that comes relatively close to the Earth. And we put this spacecraft in orbit. It took all these wonderful pictures that I showed you earlier. And then at the end of the mission, the mission team were really sneaky. They didn't announce this until they did it. At the end of the mission, they slowed down the spacecraft. They slowed it down, let it fall, until it landed on the asteroid. And it landed with its cameras pointing into the dirt, so we've got some of those pictures I showed you. You got the solar panels pointing towards the sun. They got some gamma, some analytical equipment, pointing down to the soil. So the spacecraft landed and then it sent us back an analysis of the soil. That's completely unplanned. It was not a lander, there were no feet, there was no radar to land. It was just something the dynamics people did. Just slow it down, slow it down. So that was really amazing. Here's one that's even equally. This is a Japanese mission. Hayabusa means the falcon. Everything that could possibly go wrong on a space mission went wrong. Half the antenna didn't open, the control mechanism went bust, the thing misfired, it went off into the wrong part of space. Everything that could possibly go wrong went wrong, but the Japanese, and this was their first deep space mission, somehow or another managed to hang on to that spacecraft by the skin of their teeth. They sent it to an asteroid, Itokawa, and they fired off this mechanism for picking up the sample. The mechanism misfired, the collection system went wrong, everything went wrong, and then they got the spacecraft to limp back up into space. They turned it around by some miracle. I don't know how they did it because the control mechanism was all shot. They fired it and they got it back to Earth. It landed in Australia at the Woomera missile range. And everyone said, oh, you got the thing back, but there's nothing in it because the collection mechanism misfired. So they got it back into the lab and they found that because they'd hit the asteroid rather hard, tried to collect a sample, there were tiny little dust grains around the O-wing. So they brought back 100 and something grains of dust that you need a high-powered microscope to see. So those are the first samples from an asteroid that were collected by a mission. Now in the museums we have pieces that big, right? But we know where these things came from, and we know where on the asteroid they came from. And people have done studies on those submicron particles, and we know a bit about the asteroid. And then there's this one, which is going to take off in 2018. This is one a mission that's put together by University of Arizona with Goddard Space Flight Center. And that is actually going to go out and collect samples from an asteroid. And it has a collection device, which is just a paddle on the end of a stick, and they're going to smack it down like that. And they expect to bring back 60 odd grams. So that's what I wanted to tell you about. I also want to plug my book. No one wants to buy, so I keep plugging it. There we are. Thank you very much for listening.